In this lecture, we show that integral closure is preserved under localization. So first recall what is integral closure. So you start with some integral domain A which has field of fractions k. So then A is called integrally closed or normal if the elements of k that are integral over A lie within A itself. So more succinctly, say alpha lies in k and alpha is integral over A, that implies that alpha lies within A itself. So then A is integrally closed or normal. So for here in this lecture, for alpha being integral over A, we say that alpha satisfies a monic polynomial, that it is a root of a monic polynomial with coefficients in A. So our first proposition of the lecture is this. You start with rings A and B. A lies within B and A prime is a integral closure of A within B. Now you pick up a multiplicatively closed subset of A. So let S be a multiplicatively closed, say, subset of A. Then integral closure of this localization of A at S, that is S inverse of A, is precisely S inverse of A prime in S inverse of B. So we are saying, so A is contained within its integral closure, which is contained within B. So this is what we are starting with. So this implies if you do localization, then you get this localized ring S inverse of A. This lies within S inverse of A prime, which is its integral closure, which lies within S inverse of B. So if A prime is integral closure of A, then S inverse of A prime is integral closure of S inverse of A. So integral closure of S inverse of A is S inverse of A prime in S inverse of B. So we are going to do two things. So there are two things which we prove, and that will lead to the result. So let us first outline it. So first of all, you pick up a fraction A prime over S in this S inverse of A prime. So this is localization at multiplicatively closed set S. So this fraction you pick up means that this A prime is in this capital A prime, that's the numerator is this, and denominator lies in the multiplicatively closed set. So S lies in S. So this we will show is integral over S inverse of A. So you pick up a fraction here, then we will show that this is integral over S inverse of A. So then obviously it lies in integral closure of S inverse of A. So in the opposite direction, we will show that you pick up a fraction B by S in this S inverse of B, and so obviously numerator lies in B and denominator lies in the multiplicatively closed set S. So that's why you have a fraction, and this fraction is integral over S inverse of A. So this fraction is integral over S inverse of A, then it automatically lies in S inverse of A prime. So that would prove that S inverse of A prime is integral closure of S inverse of A, because first you pick up any fraction in S inverse of A prime, it is integral over S inverse of A. And in the bigger ring, if you pick up any fraction which is integral over S inverse of A, then that becomes lies within S inverse of A prime. So lies within the integral closure. So therefore we will have this result. So let us prove this part 1 first. So first thing is, you start from here. A prime is integral over A. So you pick up an element, this A prime, within this big ring A prime, and this is integral over A. So therefore it satisfies a monic polynomial like this. So this is xn plus, say, an minus 1, xn minus 1, all the way to, say, some a0 equals to 0, where each of these coefficients lie within A. So now this A prime satisfies this monic polynomial, means that you plug in A prime here, it will give you equal to 0, you have this result. So where each coefficient is in A. So now what we do is, we are talking about this A prime over S, so you need this fraction, so you divide by Sn. So you get A prime divided by Sn. So here you have S here, but Sn minus 1 here, so you multiply it, you again have Sn all the way to Sn. Now this is another polynomial here, so you can say this is a monic polynomial like this, divided by S, then xn minus 1, and all the way to this coefficient, and you plug in this a prime over s, this becomes equal to 0. So this is root of this monic polynomial. So that implies that a prime of s is integral over s inverse of a. So notice that coefficients here in this polynomial, so this is a coefficient here, this is a coefficient here, they all lie in s inverse of a. So you can see the numerator is already lying in a and denominator is lying in s. So this one is done. So you start with some fraction a prime of s and it becomes integral over s inverse of a, and therefore it would lie in the integral closure of s inverse of a. So now for 2, so we have to show if b over s is integral over s inverse of a, this implies b over s lies in s inverse of a prime. So say b over s is integral over s inverse of a, so it has to satisfy a polynomial. So say the polynomial is x to the n plus some coefficient, say an minus 1 over sn minus 1 times xn minus 1 all the way to a0 over s0. So this is a polynomial. You plug in b over s, this will be equal to 0. So obviously it's integral over s inverse of a means the coefficients have to lie in s inverse of a, and that's precisely what we have. ai over si, each of these coefficients lies within s inverse of a. So that is just the definition of b over s being integral over s inverse of a. So we multiply this above equation by this s times s0 all the way to sn minus 1 to the power of n. So when we do that, so the first, this s to the n cancels out here, but what we are left with is s0 times s1 s2 sn minus 1 bn. So you can see clearly multiplying this entire thing by this. So you multiply this out. Now you multiply with the second factor, so this sn minus 1 will cancel out with this sn minus 1, but n minus powers will still remain. So sn minus 1 to the power of n minus 1. So again we want to repeat this complete factor here. So that's what we do, we repeat this complete factor here, but you have n powers here, so whatever is remaining from here you put it in right here. So for example s to the n you will cancel with s to the n minus 1, but you will still have s left, and then you have some powers. So again you keep on doing this. Only thing is you keep this factor as constant, and we have taken to the power of n, and as you can see, power is always decreasing because this is a monic polynomial. The leading term has this n here, so this power is decreasing, so you can always have this, and in the end you will cancel out s0 with this s0. You will have n minus 1 remaining, and then everything else is to the power of n. So now this again looks like a monic polynomial. So this you can say is x to the n. So this is just 1 here. Now this is x to the power of n minus 1 with some coefficient here, and this is just the constant coefficient. So this is just the constant coefficient. So now let us look at these coefficients. So if you look at these coefficients, you see that it consists of a's and s's. So these a's lie in the ring A, because these a's are same as these a's which lie in s inverse of a. So this lies in this ring A. So these lie in here, whereas all the s's lie in the multiplicatively closed subset S, which in turn lies within A. So all these products also lie within A. So all these products here, all the coefficients lie in A. So all the coefficients lie in A. So we indeed have a monic polynomial whose root is this entire term, s0 s1 all the way to sn minus 1 times b. So we just have shown the coefficients lie in A, since s lies within A here. So therefore this s0 times s1 all the way to sn minus 1 times b, this element is integral over A. So therefore it lies in the integral closure, which is A prime. So we are saying A prime is integral closure of A. So this immediately implies that b over s lies in s inverse of A prime. So this you can see because this numerator is s0 to sn minus 1 b. So this A prime consists of s0 to all the way to sn minus 1 b, and this denominator, multiplication of s0 s1 s2 all the way to sn minus 1, lies in s inverse. So this is indeed a fraction, and you can cancel this portion out with this portion, and there is also an s here. So in the denominator you have s0 to sn minus 1 times s. This entire thing lies in the multiplicatively closed set S, and in the numerator you have s0 to sn minus 1 times b, which we have shown lies within a prime. So we have shown b over s therefore lies within s inverse of a prime. And that is the end of the story for this proposition. So we have been able to show this. So b over s is integral over this, implies b over s lies in s inverse of a prime. So now corollary of proposition 1. So say again a is a subring of b, s is a multiplicatively closed subset of a. Now if a is integrally closed in b, this would imply that this localization of a at s, so s inverse of a, is integrally closed in s inverse of b. So this is just application of this proposition. Basically we are saying in the proposition you put a equals to a prime because a is integrally closed. So then integral closure of s inverse of a is s inverse of a prime, but a is equal to a prime, so this is equal to this. So therefore this is also integrally closed in s inverse of b. So this was the corollary. Now we come to an important proposition. So the following are equivalent TFAE on integral domain A. So number one, A is integrally closed. That implies its localization at a prime ideal. So localization at a prime ideal, recall it is something like this, s inverse of a, where s is a multiplicatively closed set which is precisely the complement of the prime ideal. So this AP is integrally closed for all prime ideals P. So this is just corollary. A is integrally closed, then S inverse of A, which is again localization, this is also integrally closed. So this is just our corollary right here. This is integrally closed. Now 2 implies 3 because maximal ideals are prime ideals. So 3 is this A localized at a maximal ideal M. This is integrally closed for all maximal ideals M. So what we have to essentially show is that 3 implies 1. Then the following will be equivalent. So to show 3 implies of 1, you start with K, a field of fractions of A, and say A prime is in K, and which is the integral closure of A. So then by our first proposition, this A prime M is the integral closure of AM. So just like S inverse of A prime is integral closure of S inverse of A, so this, instead of S inverse of A, we are writing this AM, and this we are writing as A prime M. So A prime M is the integral closure of AM. So now 3, this 3, AM is integrally closed for all maximal ideals. So this is integrally closed. So that means if you have a map from AM to A prime M, this map has to be surjective because there are no extra elements in the integral closure, because this AM is itself integrally closed, so that this map has to be surjective. So this map is onto or surjective for all maximal ideals M. Now if such a map is surjective for all maximal ideals M, this will imply that this map A to A prime is surjective. So this is a non-trivial fact which we will show in a bit. So if this localized ring AM to A prime M, this map is onto, then this map is also onto. This is surjective. Now if this map is surjective, that means ring A is integrally closed because there are no extra elements in A prime. This map is onto, so there is no extra elements, and therefore A is integrally closed. So now to prove this, notice that if you have an exact sequence like this, so this is a fact. If you have an exact sequence like this, you localize it. This is exact if and only if this sequence is exact. So localization is an exact functor. Localization is an exact functor. So this is true. So now if this fact holds, we can apply it to this sequence, this exact sequence. A to A prime goes to 0 if and only if its localization goes to 0. So if this is an exact sequence, that means this map is onto. So this is true if and only if this is true, and that is precisely what we have used here.